Yep.
So, hello everyone, and welcome to the presentation of high quality long hole drilling, which is use case number 4 in the Smig project. This project was a joint venture between Epiroc and Boliden. Epiroc provided the equipment needed, and Boliden provided the drilling location and all operators needed to execute the trial. So in today's presentation, we will look at the background and the project description. We will also look at the objectives for this project. We have a summary for performance, and to give you some insight into how the field test was conducted, we had 5 drilling locations. And the first location where we were drilling, it was basically to get up running, to start the equipment, and just to see that everything worked the way it should. And then the second drilling location, we went into more of a systematic type of testing. So different parameters were tried and tested, and we were testing the equipment quite tough. And then the third part of the field test, we were trying upwards drilling, and this was the first time it was tested with this equipment. And unfortunately, we could only do a little bit of drilling. We had some problems and some failures on the drill string. So due to safety reasons, we canceled and stopped that part of the trial. And then in the fourth part of the testing, so some findings from the systematic testing was that we realized we didn't have enough air coming from the drill rig alone. So we placed an external compressor next to the drill string in order to find out how it would perform having additional air available. And then the fifth part of the trial is called the examination hole, and that's where we applied the learnings from the previous parts of the testing, and the objective was to drill as good as possible. And then moving on into the presentation, we will look at Arrowhead, which is the framework that we use for information management in this project. And then we move on to a conclusion. How did everything go? And then included in the presentation, we have a deep dive, and that deep is details from the field test. We were testing first of all in Garpenberg, but we also extended the field test to Zinkgruvan. And the objective and the reason for that was to get more meters on the equipment, and perhaps most of all to continue to try and test upwards drilling. So then background to the project and the description. So the objective with this project is to significantly improve efficiency in underground rock excavation. And the scope with that is to increase output from the drilling and blast operation, and also to reduce the amount of requirement development work. And the target here is to double the bench height, and moving from 25-meter benches to 50-meter benches. And basically that means that we will double the output and reduce the development work in half, more or less, if this is successful. And the challenge here for production drilling is that we need to drill a lot longer holes with higher accuracy and higher hole quality. And the solution that we introduced was copper rod underground. So the objectives we had moving into this project, the first question we had to ourselves were, does copper rod work in production drilling underground? And background here is that underground is a very tough environment. Even though copper rod has been around for many years as a drilling method, it has never been tested in an underground environment. And moving underground, it also means that we need to be able to drill upwards. And again, copper rod has not been designed for upwards drilling. So in order to have equipment that works in this project, we needed to redesign the drill string, and we also needed to make modifications to the carrier in order to be able to drill with copper rod and also copper rod upwards. And another thing we wanted to find out is what potential do we have with copper rod in underground operations? And we were looking at productivity hole quality and hole straightness, and also service life of component and running cost of the equipment. We also wanted to identify what works well and what needs to be improved, and really it's about finding the requirements to make copper rod underground a commercial product, if at all possible. And also how to make relevant information available. So traditionally, it is very tricky to do monitoring of field tests with mining equipment. And the objective we had in this project was to do this using data-driven performance follow-up. So then the summary, looking at performance. So from a productivity perspective, we proved that we can drill more than 50% faster. We had a higher rate of penetration versus the reference machine, which was using conventional tube drilling system. We did realize that we have a more powerful rock drill on the copper rod machine, about 20% more power. And the conclusion still is that copper rod is a significantly more efficient drilling method. And then another important parameter here is hole straightness. And we realized that we are more or less drilling with the same accuracy as conventional tube drilling system, but we also realized that this can further be improved. We can, for example, sacrifice drilling speed in order to drill more straight. We can also redesign the drill string to do straighter holes. And then when it comes to performance of the drilling tools, in order to be more efficient in the performance follow-up, we did develop a prototype mobile application called Drill Tool Manager. And this was introduced during the field test. Some learnings from that was that the solution we have for business to consumer was a bit difficult to use. It was tricky for the operator to actually manage to log into this application, which had a delay to have it introduced. We also realized that the user experience needs to be improved. The logic in which we are collecting information from the operator has room for improvement. And perhaps the most important finding here is that we need to have off-network functionality. We need to be able to buffer data on the device in order to make this work. Another finding when it comes to the drilling tools is that the testing time was too short to get full insight into service life of the drill string. We had approximately 50% life of the drill string components left at the end of the trial. And then looking at Arrowhead, we have sort of three different components here. To the left, we're looking at the drill rig and the customer site. So from the drill rig, we have a data set available called drill quality up to the top left. And this is data that gives information of where the hole is placed, so the location in the mine. Then moving to the middle left, we have a system MVD, and MVD is measure while drilling. It is also a data set that comes from the drill rig, and it gives us all the performance parameter, how quick we are drilling, what settings have been used, and so on. And then to the bottom left, we have the drill plan, and that comes from the planning system of the mine, DESWIC. And this gives information of where the holes should be placed. And then moving on to the bottom right, we have Epiroc core services. So Assure is the system that we use within Epiroc for data storage. And connected to Assure, we wanted to have a dashboard where we can do follow-up of the performance. And then in order to make the connections, we were using Arrowhead core services. So the conclusion here, how did it go? We did find that copper rod works in production drilling underground. Very happy to see that. We also achieved more than 50% higher rate of penetration versus conventional tube drilling system. So we have a very efficient drilling system in place here. We also found out that the hole quality was the same as using conventional tube drilling system. Even though we can see here to the left, we did achieve a very accurate hole at the examination hole. a 43-meter hole was drilled with a 0.7 meter miss to target. And also to the left here, the left bar, that's the penetration rate we had at the start of the hole, and the yellow bar is the average penetration rate for the complete hole. But this is a very good achievement when it comes to hole quality and hole straightness. Another finding then is that analyzing all available data has created insights that we would not have using conventional performance follow-up. So typically, in this case, conventional follow-up, that's using pen and paper. So it was really an eye-opener having so much data available and being able to analyze that. So that's it. Thank you very much for listening, and goodbye.